Hi, my name is Naman, and welcome to my video on Taylor series. So, before we begin, we as humans love polynomials, and we want all mathematical expressions to be in terms of polynomials. They're used in most subjects and also in our everyday lives. In fact, most mathematical expressions are more intuitive in terms of polynomials. And most of this comes down to practice, but also ease of applications of rules and simplification. A simpler fraction of polynomials is often more approachable than a complex trigonometric one, for example. And what this is trying to say is that if I have a function f of x is equal to x squared plus x plus maybe 3x, it's much more approachable and easy to understand compared to a function um, more mean looking. It's a bunch of sines, cotangents, you name it. Just keep adding those trigonometric functions, which is more difficult to simplify and perhaps take derivatives of or apply into real world applications. So now let's get to Taylor series. How might we want to find an approximation for the function cosine of x in terms of polynomials? How would we approach simplification? Now, without using any Taylor series, we can already gain an invaluable intuition into what we would expect from an approximation. So take, for example, an isosceles triangle ABC with equal sides of magnitude 1 and apex angle of theta. We can already say that let's find this straight line BC, which we'll call x. And we'll also find this arc length BC, which is also x, but we'll call it x2, and the original one, the straight line, x1. We can solve for the straight line x1 by applying the cosine rule, which is all well and good, and we've done it multiple times. And we can also solve for the arc length using the definition of radians, namely r times theta, where theta is in radians, and I should have mentioned that before. Well, okay, we can now notice two important things about this expression. Is that, well, as theta decreases, as my theta gets smaller, like here, and I draw my new B prime C, my arc length approaches my straight line BC. But if you notice, there's always some extra that my arc length is. It's always a tiny bit longer, namely that x2 is greater than x1. So I can set up an inequality in terms of x1 and calling this x2, and we can simplify. So this is the x1 and this is the x2. We square both sides and we simplify. And we obtain a very friendly looking expression for cosine theta. Cosine theta is always greater than 1 minus theta squared divided by 2, which indeed is an approximation. And this solution we like. We like it because it gives an approximation in terms of polynomials and removes the trigonometric function because we could just use this right-hand side and it would give approximately the same as cosine theta. But we can make this more rigorous. Consider instead that we take and model any function as f of x as follows, where we say that we have a infinite amount of x terms, namely x to the power of 1, x squared plus x to the power of 3, so on and so forth, with coefficients c0, c1, c2, c3. These coefficients are unknown and we need to find them. And what we're saying is that, well, okay, this function f of x is approximately equal to cosine of x. We know from the previous example that there does exist some sort of function in terms of x's or thetas, which is namely this right-hand side that we found here. But how can we make it more general? Because there might not be a geometric interpretation of all approximations that we might want to make in the real world. So one thing we could do is that we could take the f of 0, which would reduce all of our x terms to 0 as well. Because if x is 0, x to the power of anything will be 0, and any constant multiplied by 0 is 0. So we're left with c0. And now we've gone one step closer to finding our entire function. We have the first term in our very complicated polynomial. Um, and now we need to consider how to find the remaining constants. And it's not immediately clear, But what we can do is we can say, well, okay, I'm going to take the first derivative of my function, where the constant term c0 will be removed according to the power rule, and all I'm left with is c1 plus 2c2 x plus 3c3 x squared plus so on and so forth. And if I similarly evaluate the first derivative at 0, my c2 term cancels, my c3 term cancels, and all that I'm left with is my c1 term, which is one step closer to my entire polynomial function approximation. And I can continue to take the derivative, for example, the second derivative, or even a higher order derivative to find c2, c3, so on and so forth. And something special happens. The coefficients of my c terms form a factorial of n. And we see this, for example, this is 2, and I'm taking the second. 2 factorial is 2 times 1, which is 2. I know this is not as rigorous as a proof, but it does work. And it also works with C1, C3, and I can write this down as follows. Let me take the nth derivative and evaluate it at 0. I'm going to get a c to the power, a c subscript n term with a coefficient n factorial, which is just a more complicated way of writing what we've just proved above. And I can divide both sides of this expression, what I'll call line 1, by n factorial, and I get Cn is equal to 1 over n factorial multiplied by the nth derivative evaluated at 0. We can use an alternative notation, namely that the derivative can be written as f to the power of n, which is a different way of writing the same thing. And I can say that, okay, this function that I had over here is equal to the sum of all my terms that I found. Because what we've done above is that we've found the nth coefficient. This is the nth coefficient. And I know that the nth coefficient will be multiplied by the nth x term. And the nth x term will just be x to the power of n. So I'm taking the sum, which is up to infinity, of course, following closely from this model that we have here going on until positive infinity. And I'm finding the sum of the cnth term multiplied by the xnth term. And I know that the cnth term is just what we found up here. And I've substituted that into there to obtain this general explanation for how to find an approximation of any function. Now, let's apply this to our example of cosine theta. We could say that, get a nice color here. Okay, we could say that f of theta is approximately cosine theta, where f of theta is the function to be found. We could say that f of theta is equal to c0 plus c1 theta plus c2 theta squared. And of course, noting that after a while, the extra terms do not contribute much. Because if theta is small, theta squared will become even smaller. Theta to the power 3 will be basically insignificant. And we'll keep it simple, keeping it to these terms. So first thing we can do is that we can evaluate this expression, cosine theta at 0, and we get cosine of 0, which is equal to 1. So therefore, c0 is equal to 1. We could take the first derivative of cosine, and we get negative sine. Evaluated at 0 is 0. Therefore, c1 is equal to 0. Then taking the second derivative, which is where we'll stop because that's corresponding to the theta squared term. We don't want to consider it bigger than that for now, although we can if we want to, is equal to negative cosine of 0 is equal to negative 1. Therefore, 2c2 is equal to negative 1. So then c2 is equal to a negative half. And then we can construct our function in a readable format. So f of theta is equal to the c0 term, which is 1, plus our c2 term, which is, our c1 term, which is 0, minus our C2 term, which is minus a half beta squared. This is just ignored, and we're left with 1 minus beta squared, which is exactly the same as we had before with our geometric interpretation. So this is a simple example of how we've applied our Taylor series to a trigonometric function. I urge you to now consider how accurate this approximation is. If we graph cosine of x and the polynomial derivation of on our trusty Desmos calculator, the two functions overlap perfectly in the range of about negative 0.4 to positive 0.4, noting that past this range the functions have no relation persisting. So now let's try to apply this learning to a peculiar integral that, once solved, will hopefully emphasize the power of the intuition we have just gained. So the first challenge is to try and write this nested cascading roots in a simpler format. So how we could do this is that notice that x is multiplying the root of the entire term next to it. So we could say that, well, note root a is equal to a to the half. So we can try and write it in this format. So let's see, the integral between 1 and 0, so it's a definite integral, is written as x multiplied by x, but that everything inside the bracket that x is multiplying is to the half dx dx. So everything that x is multiplying here is to the power of a third. Everything that x is multiplying here is to the power of a fourth, and so on and so forth. Now, we know from our indice rules, furthermore, I can't spell note, that a to the power of n, all to the power of n, is equal to a to the power of n multiplied by n. This works. We can do the same thing in our integral. 1 and 0, x multiplied by x to the half, multiplied by x to the half, multiplied by a third, multiplied by x to the half, multiplied by x to the third, multiplied by x to the fourth, and we go on, so on and so forth, until we have x to the power of 1 over n factorial dx. Alright, so notice how the denominator is just a factorial. We started off with 1 over 1, we went to 1 over 1 times 1 over 2, multiplied by 1 over 1 times 1 over 2 times 1 over 3, which is just 1 over the n factorial. And we go on forever like that. So now we can take the terms common, because all of these expressions have an x common. And we can write this as the definite integral between 1 and 0 of x to the power of 1 plus 1 over 2 plus 1 over 6 plus so on and so forth dx, which looks much simpler than our very monstrous looking integral over there. So we can now, from our knowledge, say that, well, this is just x to the power of sum between n equals 1 over n factorial. Getting to the stage alone is mightily impossible, but given also that e is equal to 1 plus 1 plus 1 over 2 plus 1 over 6, which I'm not going to prove here today, but is from the Taylor series, we can simplify this power to just e minus 1. So then our integral becomes x to the power of e minus 1 dx is equal to x to the power of e over e between 1 and 0, which is equal to 1 over e, which is our solution. And this is really powerful, because we went from something looking like a complete mess, absolutely impossible, to using our Taylor series in the power, which I didn't prove, but we can prove using Taylor series, and we are finished. So thank you for watching, and I hope you gained some intuition behind Taylor series. It's not completely rigorous, but it might preface as a good introduction. Um, I know Three Blue One Brown has a great video series on Taylor series as well, going a little bit deeper than I went today. So yes, thank you.